Okay, I finished up the example 2 graph here. Hopefully you did too. Double check your relative frequencies and the cumulative relative frequencies that are in there. I do want to point out, not a coincidence that this last one turned out to be 100%, since we had a cumulative frequency total of 45. Everybody is in there by the end, then 100% are in there by the end. We could take this cumulative relative frequency and we can create a graph from this. So a cumulative relative frequency graph plots a point corresponding to the cumulative relative frequency in each interval at the smallest value of the next interval, starting at the point at the height of 0, at the smallest value of the first interval. And then you connect them with the line segment. So first thing we're going to do is start with the 0, because 40 is the first one that we're going to have on here, and we're basically saying, starting out this graph, nobody was a president at 40, or prior to 40, sorry, because remember what we always say, as soon as you hit the rightmost endpoint, you're thrown into the next one. So we start out at 0. But all the way up to 44, though, should be representing 4.4% of the population of the first U.S. presidents. So I'm going to attempt to put a dot around about where 4.4% would be. Because between these two intervals, there were 40 all the way up to almost 45. We want to represent that it increased from nobody up to 4.4% of the population of presidents. I'm going to do the same thing for the next limit. We said that the next age bracket interval starts at 50, and there were supposed to be 20%. It's increasing all the way up to 20%. So I'm going to put dot at 50 and 20%. So again, we can see here's an increase from nobody up to 4.4, and from here we have 4.4%, it increased up to 20. So that by the time you are in the grouping of the 49 to the 45 to the 49 age range, you have 20% of the presidents that have been inaugurated at that age. So then at the 55, I'm going to be increasing up to 48.9%, or my best attempt at it. 48.9. And then connecting them. The next would be 60. So from 55 to 59, I need to increase up to 75.6. 75.6-ish. It's a really steep slope on these ones. So from 60 to 65, we increased to 91.1%. So that definitely tapers off, not quite as steep. 97.8%. So for sure not as steep here. And then at the end, 100% of the presidents, we said, were inaugurated before they were 75 years old. So I start at 0% because nobody was inaugurated before they were 40, and I stop at 100% because everybody was inaugurated before they were 75. So we just get this graph kind of describing this trend of not only the ages and the frequencies, but the kind of the rate of the change as they aged. So I was just saying a second ago that 0% of the first 45 presidents took office before age 40. And then I wanted to know what percent of the first 45 U.S. presidents were inaugurated before they were 45 years old. Well, we see the 45 years old here. So as soon as you're 45, you would go to the next group. So I want to know what percent was leading up to the 45. And that would be the 4.4%, the cumulative relative frequency of the first bar. The graph is growing gradually at first. It's not a super steep slope at the beginning because there's not really many presidents that were inaugurated in their 40s. There are a few, but there's not a whole lot, so it's a slow growing slope. It's hard to say. So a few presidents were inaugurated in their 40s. Most were older than that. So we don't really see much of a huge increase in the group of the 40s here, but then it kind of takes off. This section is this huge growing steepness, basically. So it's showing it's growing rapidly because most presidents were in their 50s when they were inaugurated. It shows that from the 50 to the 60 range, that one I traced a second ago, it's really growing quickly. A high percent was happening here. It's some really rapid growth. But then once we hit the 60, it starts tapering off again. So it slows at age 60. The rightmost point on the graph is above the age of 75. I kind of highlighted this earlier when I was discussing it. And it has the cumulative frequency of 100% because that's showing that everybody was inaugurated as president before the age of 75. And we can use this to kind of describe not just the percentile, the location of where somebody was. So Barack Obama, who was first inaugurated at the age of 47, that's pretty young, but this can kind of highlight, not exactly how young, but relatively how young he is. So if I kind of go to where 47 would be on this number line for the age and in years at inauguration, and kind of go up to this, you can see that kind of corresponds with the cumulative frequency of around 11 to 12%. So yes, that's young, but not considered unusually young. In statistics, it's not really considered unusual in terms of percent until you get below 5%. So his age represents the 11th percentile. We could actually calculate that if I had given you how many people were younger than that, but I'm just going to put not considered unusual. It's describing that it's young, but statistically speaking, it's not unusual. So percentiles show location. You can use it to come up with these graphs of the cumulative relative frequency plots. The other thing that we're going to do is talk about z-scores. So your notes on page 14, talking z-scores. So these come up a lot. It's sometimes called a standardized score, but it's for an individual value in a distribution, and it's going to tell you how many standard deviations. Because standard deviations, we said, was the typical distance away. So this is just how many of them away are you? And it's always away from the mean. Standard deviation is average distance from the mean. So z-scores is, well, how many of those standard deviations are you from the mean? Were you right there on the mean? Were you above it? Were you below it? How far did you deviate from the mean? We're going to calculate this by whatever data value we're trying to change. We're going to subtract the mean from it. Because if you're above the mean, when you do your number minus the number you're above, you're going to get a positive number. But if you are below the mean, this is going to turn into a negative number, and that sign's going to be helpful. It's kind of giving you like the direction of where your data value falls. But I don't want to just know how far away it is. I want to compare that to the standard deviation. We're going to figure out how many standard deviations that value actually is. You're going to see me sometimes write this as x minus x bar over s, just because it's a lot quicker to write than what we just wrote down. So those scores that we were looking at earlier when we first looked at percentiles in the other video, I went ahead and calculated the mean, the standard deviation, and then the 5-number summary, the minimum, Q1 median, Q3 maximum. I would like to calculate and interpret Emily's score of 43, and I'm going to do that in terms of a z-score. So I'm going to find a z-score for this to put it in context of where that score is. We know she's in the top percentile. Was it 86th percentile? I already forgot. We just did it and I already forgot. 80th percentile. So where do you know she's at the top? But now I want to describe how many standard deviations she is above the mean, because she is above average. So I'm going to take her score, subtract the mean, showing that she's above the average, and then I'm going to divide it by the standard deviation to figure out, well, how many 8.77s away from the mean is that? When you do this, you get about 0.86. So positive because she's above the mean, and just describing that she's not one full standard deviation away, she's a little smaller than that. When you interpret these, it needs to be interpreted in terms of magnitude and the direction. So I'm just going to say that her score, I shouldn't say she. So Emily's score is 0.86 standard deviations above the mean, which is showing that an 80th percentile score sounds pretty darn good. You are scoring better than 80% of the other students. However, that's not even one full standard deviation away from the mean. And the more standard deviations away you are, the more you're going to start being considered as unusually high or even unusually low if you're on the other end. Which means if Marshawn told you that his z-score is 1.2, what was his test score? You don't even need to find his test score to know for sure it's going to be higher than Emily's, because 1.2 is higher than 0.86. This is telling you that his score is over one standard deviation from the mean. It's 1.2 standard deviations from the mean. And to actually calculate that, I'm going to put that the answer to the z-score calculation is going to be 1.2. But I don't know what I subtracted from 35.44 to get that. And I also would have had to divide by 0.877. Sorry, 8.77 to get the 1.2. And then I'm just going to solve the equation for x. I'm going to multiply by the denominator. So 1.2 times 8.77. And then I would add the mean onto the other side so that we can say that his score would be found by calculating this, which when you do it tells us that his score is about a 46. I had to round that, but that would be his test score. There will be some textbooks that not only give you the formula for z-score, but the formula for how to calculate the actual data values. Because all we did is we took the z-score and we multiplied by the standard deviation, and then we added the mean back on. So if you want to memorize that, knock yourself out, but you could also just solve that equation. So z-scores describe magnitude and direction, how many standard deviations you are deviating from the mean. Negative z-scores are below the mean. Positive z-scores are above the mean. And that's it for now. So I want you to try the assignment to go with us. We'll definitely discuss it tomorrow, but I didn't want it to just be a dead day because I wasn't here.